Hi friends, welcome to 1 Minute Math. Today's video is a full explanation with pretty many examples of the Pythagorean Theorem. This is a geometry concept. You might be introduced to it in Algebra 1 or maybe even pre-algebra. It's a really kind of popular math concept that you'll see in a lot of different classes. Really classic one. We name it after Pythagoras, even though it was discovered long before he was ever just a twinkle in Father Pythagoras's eye. But we call it the Pythagorean Theorem, which you might know best as a squared plus b squared equals c squared. The context here is that we're talking about right triangles. So if I was going to write that in words, I would say in any right triangle, the sum of the squares of the legs, a squared plus b squared, equals the square of the hypotenuse. The key word there would be hypotenuse. See, the hypotenuse has to be the longest side of the triangle. That's the word hypotenuse means the longest side of a right triangle. And then the legs, the smaller sides, A and B, we can label either one of them A or B, the sum of the squares. So we're talking about the numbers here, the lengths of the sides. If I square those numbers of the legs and I add them up, I'm going to get the same number as I would get if I squared the hypotenuse. Let's go ahead and see why this works. A squared plus b squared equals c squared. All right, I've got a big triangle here. I'm sorry, a big square. I've got a big square and I have four little triangles here. You notice that each of these triangles is what we would call congruent. They're all just copies of the same triangle. They're right triangles whose legs are labeled A and B and whose hypotenusi are labeled C. And I'm just going to fill them in here just for funsies. I could put one triangle there. I'm going to put another one up here in this corner. I'm going to put another one down here in this corner. I'm going to put even another one over here in this corner. And do you notice what I get in the middle here? If I have one big square and I take out four triangles, that middle shape is a square. One square. And in fact, I could say its area, C, 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 C. Now I find the area of a square by taking one side and multiplying it by the other, and that's the area of any rectangle. So I'm going to say with area C times C, which would equal C squared. Now, just for funsies, I'm going to rearrange these triangles a little bit. I'm going to bring that guy down there, this one over here, this guy, bam. And now you'll notice that what I have left over, if I have one big square, again, one big square, and I take away the four triangles, what am I left with now? A small square with area A squared plus, get it, A by a medium square with area B times B, or B squared. A squared plus B squared equals C squared. This is one classic proof that the Pythagorean theorem is true. There are lots and lots of proofs. In fact, there was a US president, James A. Garfield, actually constructed a proof of the Pythagorean theorem way back in the day. Some of them are algebraic, some of the proofs are numeric, some of them, like this one, are visual or geometric, but there are lots of ways that we can convince ourselves that if I have a right triangle and I take the littlest side and I multiply it by itself, a squared. I take the medium side, multiply it by itself, b squared, and I add those two numbers together, I'm going to get the same number I get as if I would have squared the hypotenuse. That fact is really, really convenient for us when we're solving for sides of right triangles. And this page, I'm just reminding us that what really matters is that we can distinguish between the hypotenuse, which is the longest side, and the two smaller sides, which we call the legs. And it doesn't matter which one we call A and B. It really doesn't. Kind of as a rule of thumb, I generally call the smallest side A. So if we're looking at this triangle, the smallest side I'm going to call A, the middle side I call B, and the longest side I call C. Again, the only one that really matters is that I call that longest side C, and I can set up my Pythagorean theorem statement, a squared plus b squared equals c squared. This is how we're going to use the Pythagorean theorem, use that fact that we just proved with our big square and the four triangles. We're going to use that fact to find a missing side of a triangle. Right? We put a man on the moon. We should be able to do this. We should be able to figure out what the length of that side should be without taking out a ruler and measuring it. So I'm just going to replace A and B with 8 and 15. And I can type that all right in my calculator. If you want to play along, please grab a calculator and do that. Type 8 squared plus 15 squared, and I would type it just like that. You run the risk of accidentally getting the wrong answer if you pause in between there and don't do the squares right away. So now that we know that a squared plus b squared equals 289, and I know that that also equals c squared, I can find c by just taking the square root. I have to unsquare. If c squared equals 289, now I'm asking the question, like reverse engineering. What number times itself equals 289? And how we answer that question, I don't divide by 2, I don't subtract anything, I take the square root. That symbol should be easily found on your calculator. If you don't have a square root button on your calculator, you might have to hit the second button and then the squared button. Or if you're using a phone calculator, you might have to turn it sideways and look around at the options that you have. You might even see it with a little 2 on it, a 2 and then that garage looking symbol. This is the square root. That's what we're doing. We're unsquaring a number. I type this in my calculator, it gives me the number 17, and that's how I know that x equals 17. So just for funsies, if I had 2 other numbers, I'm going to square them. If I'm looking for the biggest side, just type that in my calculator, take the square root of the number it gives me, and that is my answer. That's my longest side. Okay, now what if the number that we're looking for is not the longest side? So let me go through an example here where I've got a is the number that I'm looking for and not c. So I write out my a squared plus b squared equals c squared again, but now a is a variable, it's x. So when I do this next computation, when I run my calculator to crunch some numbers here, I can't do one step. I can't do 15 squared plus 21 squared. I have to take them one at a time. 15 squared is 225. 21 squared is 441. X squared plus 225. So I'm going to do a little bit of algebra to get x alone. I'm going to subtract 225 from both sides, and I get x squared equals 216. Again, I take the square root on my calculator, square root of 216. Now, 9 times out of 10, if you're doing a Pythagorean theorem problem and you do the square root step, you are not going to get a nice number like 17 or 10 or 12, or it's not going to be a nice whole round integer. It's going to be something funky. If you've got a really nice calculator, when you type in the square root of 216, it will tell you this: 6 roots of 6, or 6 times the square root of 6. That's what we call the simplest radical form of this answer. That's a great way to report your answers. If you're on the SATs, this is the way that they're going to offer answers to you, not decimal values. So if your calculator gives you this number, don't immediately think that your calculator is wrong. Report that answer. Write that down on your homework. Show your teacher. They'll be really proud. But if your calculator does give you a decimal like 14.7, that would be the decimal answer to this one. That's fine too. Okay. Sweet. So let's do one more example of those just for funsies. Let's say I had 34 and 16. Okay. And now I'm looking for a side that is not the hypotenuse, not the longest side. If we kind of extrapolate what we did in this last example, I'm going to do 34 squared minus 16 squared. If you want an easy way to do this in one step in your calculation, you may do, like, instead of a squared plus b squared, you're going to type in c squared minus a squared, c squared minus b squared. And that's going to give us 9,000,000. There we go. I think 90,000. Let me check. Might be only 9,000. 34 squared take away, oops. 34 squared take away 16 squared. 900. Wow. I was way off. Boop. Then we take the square root of that on your calculator, square root of 900, and that gives you 30. And that would be your answer. Cool. 2 other quick things to see here before we close this video out. One is the converse of the Pythagorean theorem, and then we're going to look at a couple of what we call Pythagorean triples. The converse of the Pythagorean theorem, instead of saying, if I have a right triangle, then a squared plus b squared equals c squared, the converse says, if a squared plus b squared equals c squared, then my triangle is a right triangle. If the sum of the squares of the two smaller sides equals the square of the largest side, then the triangle's a right triangle. And notice how I said largest side here and not hypotenuse, because we're not sure yet if it's going to be a right triangle. Here's how I would use that fact, this converse of the Pythagorean theorem. Let's say I've got a whole bunch of triangles here, and the question is, which of these are right? They all look like they're right triangles. I am not going to tell my teacher, well, this looks like a right angle, so it's going to be a right triangle. Maybe it's 90.4 degrees. Maybe it's 89.8 degrees. And to be sure that it's actually 90 degrees there using the numbers, I'm going to check, is a squared plus b squared equal to c squared? I put a question mark over that equal sign because I'm not sure that that statement is true yet. Now I type in my calculator, what's 29 squared plus 41 squared? And my calculator tells me that those things are 2522. Then I'll ask my calculator, what's 49 squared? And it tells me that that's 2401. These are not equal. This is not a right triangle. If it were a right triangle, those numbers would be equal to each other. They're close. They're in the same neighborhood, but they're not equal. Let's check one more. Let's just check this buddy up here. And again, I'm going to check the two smaller sides and see if I square them and add them up, will they be equal to the largest side squared? 3.5 squared plus 12 squared. My calculator tells me that that is 156.25. 12.5 squared is also 156.25. Those are the same, and I can conclude that this is a right triangle. Right? That's how we use the converse of the Pythagorean theorem. I could even go so far as to say this 2401, this longest side, it's too small. Not only is it not equal to a squared plus b squared, but it should be bigger. It's too small. That means this triangle is actually acute. So the angle might be like 89.4 instead of 90 degrees. All right, last thing here is Pythagorean triples. You might have noticed some patterns in some of the triangles that we saw. For example, 3, 4, 5. You can check this if you want to. 3 squared plus 4 squared is 9 plus 16 is 25. 5 squared is 25. 3, 4, 5 always makes a right triangle. That's a fun little fact. So the handy part about that is, let's say I had another triangle over here and it said 30, 40, and the question was, what's this largest side? It's as easy as you think. 3 times 10, 4 times 10, 5 times 10. Or maybe I have another triangle over here that says 6, 8, question mark. 3 times 2, 4 times 2, 5 times 2. So when we have a Pythagorean triple like 3, 4, 5, what we're saying is any triangle that fits in the family whose sides are any multiple of 3, 4, and 5 together, that triangle will be a right triangle. And we can exploit that fact to make short work of Pythagorean theorem problems if you're in a pinch. This often comes up on the SATs as well, where it gives you something like 15, 12, and you're looking for this last side. And if you can recognize that they are multiples of 3 and 4 and 5, then you can come up with this side pretty easily. So this list over here, these are Pythagorean triples that if you have space in your brain to memorize them, I would definitely memorize 3, 4, 5. That's an easy one because the numbers are right next to each other. 3, 4, 5 is a really common one to know. But again, if you have any space in your brain files to store a few, in order of importance, I would include these other 3. 5, 12, 13 is another really common one. 7, 24, 25. In fact, 7, 24, 25, that's how I knew this triangle right there was going to be a right triangle without even doing any computation. 3.5, 3.5 is 7 divided by 2. 12, 24 divided by 2. 12.5, 25 divided by 2. 3.5, 12, 12.5 is a 7, 24, 25 family triangle. So the fact that I had this memorized meant that I could really easily tell that that was a right triangle without doing any computation. I realize that that's easy for me to say because I'm a math teacher. I see these things all the time. But if you can find the space in your brain files to memorize these 5, 12, 13, 7, 24, 25, and 8, 15, 17, I think you will find it helpful. All right, that's it for this video. I hope that you found this video to be helpful for you. Keep on watching. I hope to see you next time.